Welcome to the next tutorial in electrical machines. We are going to discuss the few problems based on alternators. The problem 1, calculate the pitch factor for the following cases. So we need to determine the pitch factor when the construction of the alternators are given to us. So the construction of alternator under 3 categories are 36 stator slots, 4 poles and coils spanning from 1 to 8. The second one is 72 stator slots, 6 poles, coils spanning from 1 to 10, and 96 stator slots having 6 poles, coils span 1 to 12. So in the slots of the stator, the coils are present, and we know that two conductors, or rather we say the two turns, will make one conductor, and these conductors will be present in the slots forming the coil. So we will be determining the pitch factor for the cases. So let us see the 3 cases. So case number 1, we can see that the numbers which we are given here 1, 2, 3 and so on, which are present in the form of the slots, and the conductors. So this is the conductor where 2 turns are there, and it is present in the coil number 1, that is slot number 1, and the slot number 8. So in the slot number 8 and slot number 1, the conductor is being formed. And in the other case, you are having the total spanning from 1 to 10. So you will be having the slot number 1 and slot number 10 as the total spanning of the conductors. Other cases, as usual, we can form for coil spanning of 1 to 12. Now when we have 180-degree pole pitch, then in that case we are getting the maximum EMF in the conductors. So let us see how to determine the coil pitch for this particular factor. So in the first case, if we see that there is basically coil spanning from 1 to 8, it means that if the 10th slot, which is resulting in the formation of the total 180-degree pole pitch, then in that case the coil is shortened by 2 slots. So from 8 to 10, this is the slots where the coil is shortened. So the coil span will fall short by 2 slots, and the total number of slots is, which we have here in this case, is 9 into 180 degree, that is resulting in 40 degree. It means for alpha 40 degree, we know the formula for the pitch factor or the coil span factor Kc is equal to cos of alpha by 2, which we have studied in the lecture class. So here we can determine what is the value of Kc. So K cos of alpha by 2, which will give us 0.94. In the other case, where you have a total 72 stated slots, then in that case, since the coil spanning is occurring from 1 to 10, in that case the shortened coil is 3 slots. So total 3 slots are being shortened, and in that case we can form 3 by 12, because 1 will be forming 12 as the total number of slots forming one conductor, and then into 180 degree, which is equal to 45 degree. Hence, the value of coil span factor is cos alpha by 2, which is equal to 0.924. Third case, where the spanning is between 1 to 12. So in that case, we have total shortening of 5 divided by the total slots, that is 16 into 180 degree. We are having the angle 56.16, and hence the pitch factor is 0.882. In all the cases, we can see that the coil span factor Kc is basically less than 1. Let us move to the problem number 2. Here we need to determine the value of Kd, which is the distribution factor when the windings are distributed in the different slots. Now the alternator is having 9 slots under the influence of a per pole, and the following cases we need to determine the Kd value when winding are present in all the slots. One winding is present only the first 2 by 3 of the slots per pole, and when 3 equal windings are placed at sequentially 60-degree phasor group. Let us find for all the three cases what is the value of Kd, that is the distribution factor. We know that the formula for Kd is sine m beta by 2 by m sine beta by 2, where these nomenclature we have already studied in the lecture class. So let us find the value of beta. So the value of beta for the different slots, which is equal to 9, 6 and 3, these we are getting for all the three cases respectively, because here we have 2 by 3. So 2 by 3 multiplied with 3, 2 will give me 6 and 3 and 9 respectively. So beta, which is equal to 180 degree by 9, is equal to 20 degree, and for all the cases we will find one by one what is the corresponding beta and what is the corresponding m for the particular case. Once we know that what is the value of m and beta, we can put this value in the equation of Kd and we can determine the value of Kd for all the cases. So for the first case, putting the value of m to be 9 and beta to be 20 degree in the equation of the distribution factor, we get the value as 0.64, and for the second value, substituting the value of m to be 6 and beta to be 20 degree, we get 0.83 and 0.96 for the third case as usual. Here we can see that Kd is also less than 1. So we have found out in the first two problems the values of Kp and Kd. So pitch factor and the distribution factor. Kp is also known as Kc as the coil span factor. Problem 3, let us see. Here you have a part of an alternator winding which is consisting of 6 coils in series. So coils are wound in series and there are total 6 coils. Each coil is having an EMF of 10 volt RMS. So this is for one coil. And the coils are placed in the successive slots, and between each slot and the next there is an electrical phase displacement of 30 degree. So phase displacement is 30 degree between the slots. You have to find the EMF of all the 6 coils which are connected in series. So here the beta is 30 degree, m is 6, so we can easily find Kd value from the second tutorial problem, how to find sine m beta by 2 by m sine beta by 2. That will give me the value of Kd, and hence we know that the Kd is nothing but the arithmetic sum of the EMF by the vector sum. So this is the arithmetic sum of the EMF by vector sum of the EMF, and we have the other way around, that is the vector sum by arithmetic sum. And in this case, what do you have is that the Kd will be less than 1, and hence the arithmetic sum of the voltage induced in the 6 coils are basically 60 volt, because we have 6 coils in series and there is 10 volt RMS per coil. We have total 60 volt, and the vector sum in that case will be equal to Kd into arithmetic sum, because we have seen the equation of Kd is nothing but the vector sum by arithmetic sum of the induced EMF. Vector sum will always be less than the arithmetic sum, hence the Kd value will be less than 1. We have found the arithmetic sum, we can put it in the here arithmetic sum as 60 volt, and the value of the distribution factor, which is in terms of Kd, we have to find out, which we get to be 38.64 volt as the vector sum of the EMF. Next problem whatever we have is, if you have a 3-phase 50 Hz alternator which is running at 600 RPM, and it is a 2-layer winding, so it is a distributed type of winding, and there are 12 turns per coil, 4 slots per pole per phase with a coil pitch of 10 slots. Determine the induced EMF per phase if the flux per pole is 0.035 Weber. So EMF you need to determine per phase, where the alternator is a 3-phase alternator. It means that whatever the line voltage and phase voltage consideration we need to do. So always the line voltage will be equal to root 3 times the phase voltage, and this phase voltage is what we have to determine. Now here the number of poles we can determine directly from the equation of the synchronous speed of the alternator, which is equal to 120 F by N, and the frequency of the supply is 50 Hz, and the speed with which the alternator is rotating is 600 rpm. So the number of poles is basically 4. Now here, what is the total slots that we have? Now the total number of slots, if we can see from this equation, it is 4 slots per pole per phase. So number of pole we have calculated as 4 and number of phase is equal to 3. So this is pole, this is phase, and multiplied with the total slots what you have the coil pitch, that will give you the total number of slots. So it is equal to 120. Now beta, which can be obtained as 180 degree by into coil pitch by total number of slots, and the coil pitch that you have is given as 10 slots, and the total number of slots that we have determined is equal to 120. In that case, the beta is 15 degree, and the KD equation sin m beta by 2, where the value of m is given as 4 and we have beta is 15 degree by m sin beta by 2, which is 0.958. So the pole pitch we have to determine, which is the total number of slots by coil pitch, which is equal to 12 slots. And this alpha, the cording angle, which is the less coil span angle, will have 12 total number pole pitch minus the slots of coiling into 15 degree. We have total 30 degree as the alpha. So Kp value is cos alpha by 2, that is equal to 0.966. And hence the EMF equation which is we can obtain per phase for the alternator is 4.44, frequency into number of turns per phase multiplied with Kp and Kd. Kp and Kd we have already determined, and hence we can put it in the equation. Number of turns is given to us, and hence we get the RMS value of the EMF. Problem 5th. We have a 3-phase 16 pole alternator which is star connected. So since it is a 3-phase alternator, it may be connected in the form of star or delta. It is a 3-phase alternator, it is connected in the form of star with total slots as 144 and 10 conductors are present per slot. The flux per pole is given to be 0.03 Weber, which is sinusoidally distributed, and the speed is given as 375 rpm. Assuming a full pitch coil, you have to determine the frequency, the speed, and the phase and the line EMF for the particular alternator. So first let us see how to find the frequency. Frequency we can find from the equation of the speed, which is Pn by 120 degree, which will give us 50 Hz as the frequency of the supply, because poles and the speed are given to us. In this particular case, we have not been given the full pitch, it is given. So Kc value we can take as 1 because it is not given that the coil is short pitched. And hence, the number of N value we can determine from the slot angle, which is 144 by 16, which is equal to 9. And the other terms, which is equal to beta, is 180 by 9, which is equal to 20 degree. And m we can determine as usual from the previous cases, which is equal to 3 in this particular case, and hence the Kd value we can get as sin m beta by 2 by m sin beta by 2, which is equal to 0.96. Once we know the Kd, now the total number of conductors we can find out. So we always know that the 2 turns will be making 1 conductor, and depending upon how many slots are there in the alternator, depending upon that we can count the total number of conductors, which is 480. So 480 conductors means 240 number of turns per phase, because we have to divide this with 2 to determine the total number of turns, and then we can put it in the EMF equation, which is 4.44 into Kp Kd number of turns frequency, which is equal to 15.34 volt. Now the line voltage is basically root 3 times the phase voltage for an alternator for a 3-phase machine. So it is equal to 2658 volt. Problem number 6. Find the no load phase and line voltage of a star connected 3-phase 6-pole alternator, which is running at 1200 rpm, having the flux per pole of 0.1 Weber, which is distributed sinusoidally. The stator has 54 slots having double layer winding. Coil is having 8 turns and the coil is corded by 1 slot. So 1 slot it is being sorted which is having a total of 54 slots, and each coil is having 8 turns that is being given to us. So what is the short pitch angle we need to find, which is equal to 20 degree, because only one slot it is being sorted. Now the Kc value, which is equal to cos alpha by 2, which is equal to 0.98, and the frequency we can determine from the speed, which is equal to 60 Hertz. And once we know the frequency, the other terms as usual, the n value and the beta value and m, we can determine. Once we know these fundamental quantities of n, beta, m, similar to the previous problems, we can determine the value of Kd, which is sin m beta by 2 by m sin beta by 2, which is equal to 0.96. And hence the total number of conductors Z we can determine as 144, and the turns will be half of the total number of conductors. That we can put it in the EMF equation as 4.44 frequency, number of turns, Kp and Kd. So the line voltage again will be root 3 times the phase voltage, which is equal to 3.25 volt. Problem 7. Calculate the RMS value of the induced EMF per phase of a 10-pole 3-phase 50 Hz alternator with 2 slots under the influence of per pole per phase. 4 conductors are per slot in 2 layers. The coil span is 150 degree. So the flux per pole has a fundamental component of 0.12 Weber and 20% third component. So harmonics are present in the fundamental component, and the third component of harmonics are present, which is 20% of the flux per pole of the fundamental component. So here we need to find the RMS EMF for both the fundamental component of the EMF and the harmonic component of the EMF. So the problems that we have dealt in the previous few were to determine the fundamental EMF. So the first case remains the same as usual, how to determine, that is, what is alpha, the coding angle, the shorten. So it is 150 degree spread, so 180 minus 150 will give you 30 degree. The value of Kc is cos alpha by 2, m is given to be 2, number of slots per pole is 6, so beta is nothing but 180 degree by 6, which is equal to 30 degree. Now Kc we have determined, so we'll determine Kd now, which is sin m beta by 2 by m sin beta by 2, which is equal to 0.966. Total number of conductors whatever is present in the slots, that is equal to 80, and hence the turn per phase will be half of that, which is equal to 40, because again the 2 turns will make 1 conductor. EMF per phase equation, we can put 4.44 Kc Kd frequency flux into number of turns, and hence the fundamental component of the EMF is 995 volt. Here no harmonics are present. In the second case, we need to take the effect of harmonics. So when we take the effect of harmonics, the equation of Kc and Kd will change, because here the third component of harmonics will come. So cos n alpha by 2, which will be 0.707, and here also in the equation of Kd, there also will the third harmonic will come, which is equal to 0.707. Now the frequency Fn for the harmonics is equal to n times the fundamental component of the frequency. So which is equal to 150 Hertz, because third harmonic is present, and the flux we have been given the 20% of the fundamental flux, and you have 1/3 of that, so it is equal to 0.08 Weber for 0.12 Weber as the fundamental flux, which we can put it in the EMF equation for the harmonic EMF, which is equal to 106 volt. Now the total EMF per phase will be comprising of the fundamental EMF plus the harmonic EMF. So it will be a vector sum of E1 and E3. So E1 is the fundamental EMF and E3 is basically the EMF due to the harmonic component. So we can find 1000 volt as the EMF per phase. Now note here that whatever the EMF we are getting under the influence of third, ninth or 15th harmonic, we are eliminated from the line voltage. The line voltage are star connected network will be 995 into root 3. So 995 is the phase voltage. If you multiply it with root 3, you will get the line voltage, and harmonics will not be present in the line voltage. It is only in the phase voltage the harmonics will be present. So line voltage will be free from the harmonics. So this completes the first tutorial on alternators, and the coming two tutorials we are going to discuss the problems related to the voltage regulation and the problems related to the fundamental EMF finding. Thank you for now. See you in the next tutorial.